Welcome to the Deep Dive. Today, we're on a pretty fascinating mission, actually. We want to peel back the curtain on imaginary numbers. To figure out why this concept, which sounds kind of dismissive, right? Imaginary. Why it's actually, well, the hidden engine driving so much of the modern world, your phone, quantum physics, all of it.
It's fascinating because unlike a lot of math concepts that people just sort of develop for fun or abstract thought, imaginary numbers, things like the square root of -1, they weren't really sought out. They were kind of forced into existence back in 16th century Italy.
Right during that really intense period with the competitive mathematicians, Scipione del Ferro, Tartaglia, Cardano, all racing to solve the cubic equation.
Exactly, that whole secret-keeping competitive environment. And Cardano, he published the winning formula, but it came with a big problem, a sort of mathematical ghost.
Yeah, the paradox. Because sometimes the formula, even for equations they knew, had simple, real answers.
Right, like $600 plus $400, they knew $600 was the solution, a perfectly real number.
But Cardano's formula made you calculate something impossible midway.
Precisely. You'd hit a point where you needed the square root of a negative number, like square $121. It was this impossible step needed to get to a perfectly real answer. Cardano himself just called it mental torture.
I bet. And most people just threw up their hands, right? Ignored it. It's pretty ironic that this secret, closely guarded method depended on impossible math.
Well, until Raphael Bombelli came along, he was an engineer, more practical-minded, and he had this really wild thought. What if we just treated these impossible roots as if they were real, like usable things?
Just run with it.
Yeah. His key insight was seeing that these two weird parts, the $2 plus scored $121 and the $2 scored $121, if you added them together.
The square root parts, the imaginary bits, they'd cancel each other out.
Perfectly. Vanished, leaving just the real number, 2 plus 2, which is 4. The known answer.
Wow. So he basically showed you had to go through this imaginary realm to get back to reality sometimes.
He did. But people still didn't like it conceptually, which is why, decades later, René Descartes gave them that name.
Imaginary.
Yeah.
Yeah, it sounds pretty dismissive because you couldn't picture it.
That was the block. Positive numbers, negative numbers. They live on a line, right? A number line. Easy. But where does Allah, the square root of -1, actually go? Squaring it gives you -1, which is on the line, but where's the I itself?
So adding a new dimension, this geometric fix, was it just a clever trick or something deeper?
Oh, definitely deeper. The geometric view, which Gauss really pushed, though Wessel and Argand had the idea too, was just to say, okay, add another axis perpendicular to the first one.
Making the complex plane 2 dimensions.
Exactly. So a number like $3 plus 4 eyes isn't some mystical entity. It's just coordinates. An address on a 2D map, like 3 for...
And that map unlocks the rotation idea. This is cool. We know multiplying by -1 flips you 180 degrees on the number line.
Right, a full half turn. So all dollar must be the thing you do twice to get that 180-degree rotation.
Which means multiplying by $100 is just rotating 90 degrees counterclockwise.
You got it. So 8 times I dollar, doing that rotation twice, lands you at 180 degrees, which is -1. So I times isn't some arbitrary rule. It's just geometry. What happens when you turn 90 degrees twice?
Okay, geometry's elegant. But now, the payoff. How does this rotation thing, this 2D number, become this indispensable engine for technology, the 2-in-1 power?
Well, think about what that 2D map gives you. A point on that map has a distance from the center, the origin. That's its magnitude, like signal strengths or amplitude. And it also has an angle relative to the positive real axis. That's its phase. Think timing or, well, angle.
Magnitude and phase. Got it.
Right. And complex numbers package both those things, magnitude and phase, into one single number. Anything that oscillates or involves waves needs both. Radio waves, sound waves.
AC power.
Yeah.
The electricity in our walls.
Absolutely. Alternating current is constantly shifting its voltage and current, both magnitude and phase. Analyzing that with normal math means really messy differential equations, calculus over time. But engineers use complex numbers. They call them phasors. It lets them basically freeze that wave in time and represent its magnitude and phase with one complex number. So those horrible calculus problems, they become simple algebra. Like Ohm's law, but slightly fancier, VIZ.
Voltage equals current times impedance. And that Z, the impedance, is the complex part.
That's it. Z bundles up the resistance and all the tricky phase shift stuff caused by capacitors and inductors into one value. It makes designing every electrical circuit possible, basically.
Okay, that's huge.
Yeah.
So from circuits all the way to quantum mechanics, you mentioned the Schrödinger equation. Was that I in there just a mathematical convenience for a while?
For decades, that was a real debate. Is the imaginary part, the I, truly necessary to describe reality, or just a useful calculation tool that, disappears in the final answer?
Eh,
The debate seems to be, well, pretty much over now, thanks to some really clever experiments recently. They used quantum entanglement to test theories that tried to describe quantum mechanics using only real numbers.
And they failed.
Conclusively, it seems you cannot get the results we see in nature without that imaginary component. It's not optional. It appears to be a fundamental part of the universe's, I guess, mathematical language.
Wow. So the name imaginary is just completely wrong. It's one of the most real things there is, mathematically speaking.
It really seems that way. It's arguably the greatest misnomer in science. Think about it. The same mathematical logic that cracked a 16th century algebra puzzle.
Is woven into the fabric of how subatomic particles behave.
Exactly. Which really leaves you with a pretty profound question to ponder, doesn't it? If this concept, once totally dismissed as impossible, as imaginary, turns out to be absolutely essential for describing reality, what else are we currently dismissing today? What other impossible ideas might just be waiting for us to figure out their deeper fundamental truth?